universo, no solo el espacio, sino también del tiempo. Nuestro plenarista del día de hoy, el doctor Alan Strauss, es originario de Tucson, Arizona, que es uno de los estados en Estados Unidos donde más se ha hecho astronomía en el mundo. Él hizo el doctorado en la Universidad de Arizona en Educación y Difusión, Education and Public Outreach, y se ha involucrado en el Observatorio Vera Rubin y en el Legacy Survey of Space and Time. Entonces, con esto ha conjuntado sus dos intereses, y una de las metas que busca el doctor Alan Strauss es la participación de todo el mundo, abrir este proyecto no solo a la comunidad astronómica, sino a la ciencia ciudadana y a toda la gente. So, I'll switch to English. Dr. Alan Strauss will give you the talk in English, and I hope students will be okay with that. Cuando termine la plática, para las preguntas se las pueden hacer directamente en inglés o se las puedo yo traducir, ¿no? So, I won't take more time. Dr. Alan Strauss, the floor is yours.
Okay, can you hear me? Yeah, even better. Okay, I apologize that my whole talk is in English. I grew up 100 kilometers from the Mexican border in Arizona and somehow never studied Spanish in school. So here I am. I'm good with food words and numbers and colors, so if you want to go out to eat later, that we can do. Better? Okay, and the laser pointer. Yeah, so I'm the head of education and outreach for the Vera Rubin Observatory, which is just finishing construction in north central Chile. And you can see a picture of it there in the desert. And so my job today is to give you a little update about the observatory and hopefully get you all as excited about it as I am. So that's what we're going to talk about, is a little overview of the observatory. I'll give you a little status update on where things are. I said it was nearing completion. It's a pretty exciting week at Rubin, actually. So we will talk about the education and outreach programs broadly. We'll talk a little more specifically about the formal education that we do. So these are things for teachers and students in high school and college. And then about citizen science, which is a very unique and big part of Rubin. How many of you are students? Come on, don't be shy. I worked at a university for 20 years. Okay, that's great, because this observatory is really for you, right? The data that's going to come out of Rubin is going to be the next, I don't know, 20, 50 years, maybe I'm optimistic, of research will be done with this. So, what is the Vera Rubin Observatory? It's a really big telescope. That's all you need to know. So first, I want to tell you where it is. I mentioned it's in north central Chile. There's the laser. So here's Chile, very long country, about most of South America, as you can see. And so there's a little red dot there in north central Chile. That's where the telescope is. It's about 3 hours drive north of Santiago, if you've been to Santiago. And then a little closer up, it's about 100 kilometers from La Serena, which is a port. And it sits at about 2,660 meters in altitude. That's at the top of the pier, actually, that the telescope sits on. So a little bit of history is that this observatory was envisioned over 20 years ago. And in the United States, every decade, every 10 years, the national academies issue a report, recommendations in astrophysics for the priorities for the coming decade. And Rubin Observatory, which was not named Rubin Observatory at the time, was the top priority in the 2010 decadal survey for astrophysics. And it's funded by two agencies in the United States, the Department of Energy Office of Science and the National Science Foundation. They each provide right about 50% of the funding. There we go. So what are we up to? Well, there are 4 main science goals of the observatory. We won't go into great detail on these because I have way too many slides. But these are them. There's dark matter and dark energy, cataloging the solar system, understanding the Milky Way structure and formation, and exploring the transient sky. So I hope you're wondering, how does one observatory do all of this? Right? Well, it has to work very quickly. So that's what we're going to talk about today. So it's going to carry out what's called the LSST, which is the Legacy Survey of Space and Time. That was the original name of the telescope. We'll talk about the name change soon. And that survey is going to be a 10-year time lapse of the entire sky as seen from Chile. It's an optical and near-infrared survey in 6 bands. And it looks like when I converted this to PowerPoint, the graphic ran over a little bit. But it's going to image each area in the sky approximately 800 times. Some up to 1,000, a little more, some a few less. And it's going to do this continuously, relentlessly, for 10 years. And what that's going to result in is a giant catalog of around 6 million solar system objects. Compare that to maybe 1 million that we have now. Right? About 18 billion stars, 20 billion galaxies. And each of these will have exquisite photometry, astrometry, and image quality. Nothing like this has ever been done before. So what makes it special? Well, what makes it special is the ability to do this survey, right? So it's got an incredibly large field of view. The sensor on the camera has 3,200 megapixels. It's the largest digital camera ever built. And it's about 3.6 degrees across. It's the field of view. It's an 8.4 meter mirror, and that compares with the largest mirrors we have now. So this is a graphic I stole off the internet. If you do a search on telescope mirror size comparison, you'll get this very image. And so I circled in red our mirror here, but you can see it's about the same size as Gemini South, Gemini North, Subaru telescope. This is the large binocular telescope in Arizona. It has 2 mirrors that size. So right now, there are very few mirrors that are bigger. Soon, we hope, the giant Magellan telescope will be built, which will have 7 mirrors of similar size. This is the European Southern Observatory's extremely large telescope, which is also under construction. So it's pretty big. Speed. Are you sitting down? Okay, good. Every 3.5 nights, it will have surveyed the whole sky in all 6 bands, through all 6 filters, right? So the cadence is a little challenging to explain, but essentially it could scan the whole sky in half a night. That's how wide and fast the telescope moves. What's also special, perhaps most special, is that the data will be widely available. So most telescopes, as you know, you apply for time and you hope that the allocation committee grants you time and that there are no clouds on the night that you're there. This is very different. The data will be made available in annual releases to everyone that has data rights. Okay, so you're going to hear, if you follow Rubin a lot, this saying, wide, fast, and deep. That's how we're carrying out this ambitious 10-year legacy survey. So it's going to be wide. It's going to image the entire sky, 18,000 square degrees every 3 nights. It's going to take an image about every 20 seconds. That's fast. For 10 years to go very deep, continuously. The result, an 800 to 1,000 frame time lapse in 6 filters of 40 billion objects. Every one of those objects will have a little time lapse, a big time lapse. And then this is just a kind of a map you can see of the current survey strategy. And the yellow areas are the wide, fast, deep, and then the blue and green are some other survey speeds. So here's a little, some images of the observatory. Here you can see the telescope in construction. And a little bit for scale, this is the front of the camera with the camera crew when it was in the clean room in California. It was assembled at Stanford University, and it's the Department of Energy that funds the camera. And then here's a cutaway of what the building looks like. So the ground floor is the machine shop, and then the second level here are the control rooms and offices. And then level 3 is where a lot of the fun things are. And you can see in this graphic that this is the coating chamber where we coat the mirror with protected silver. They have the mirror sitting here in this graphic and some other stuff. And then in the back here, there's actually a clean room for the camera, in case the camera ever has to come off the telescope for maintenance. This is a 27-meter platform lift. This is how we move the mirror, for example, up from the coating chamber to the observatory floor. It's really neat because when it comes up to get into the observatory, the whole roof of the elevator lifts off. So on those days when they have it open, you have an amazing, beautiful view of the mountains. And then here, of course, is the telescope and the dome, which is about 30 meters tall. Okay, wide. So here is the telescope. Now, I can tell you that you are seeing a picture of the telescope that nobody has seen yet. Wait, what's today? Today's Monday. Today is the day that people are seeing it. And why is it special? Well, this is on one of my later slides. But Friday, the primary mirror was installed for the first time. So we're really excited. The first rock was blasted out of the mountain in 2015 in the summer. In June, Northern Hemisphere summer. So it's been about 10 years to get to this point, and we're very close. So, oops, wrong button. So the mirror sits down here, and you see that we call it M1, M3. That's because it has 2 surfaces. Most telescopes, that first mirror, the primary, just has one surface, and the light reflects up. Here, you can see that there's an outer surface, this ring, and then there's an inner surface, which has a steeper curve. And the second mirror, M2, is up here, which it's hard to see in the picture. But so the light from the sky comes in, hits this outer surface, comes up to the secondary, comes down to the third surface, and then up to the camera there. So that's why we call this M1, M3, and M2 up there. And that was new. Nobody's ever made a telescope with this optical design. It's very, very fast. It's about f1.3, I believe. So you can see 8.4 meters. The inner surface is about 5 meters across. The secondary up here is 3.5 meters. And they all have actuators on them to deform the mirrors slightly. Come on. There we go. Okay. How else do we get wide? Well, we have this amazing camera, the biggest one ever built. 3.6 degree field of view. And so this is really important for time domain science and to enhance the probability of detecting rare events. The more sky that we can see at one time, right, the better our chances. It was a very challenging optical design. We talked about the 2 surfaces on a single piece of glass. It's the largest camera. 189 CCDs, 3.2 gigapixels, and it reads out in 2 seconds. Right? Everything is very fast. Okay, 3.2 billion pixels. How many pixels is 3.2 billion? We can't even conceive of it, right? So it would take about 400 ultra-high definition TVs to display one image from the telescope, right there. If we were going to view all the images from the 10-year survey at 30 frames a second, it would take about 11 months to watch that. So we keep saying it is the greatest movie of all time, next to Star Wars, we know. Okay. And it's fast. I've said this, right? Wide, fast, and deep. So to survey the sky in 3 nights, it has to be able to move quickly as well. And so it can move 3.5 degrees on the sky and be ready to open the shutter for the next image in under 5 seconds. It's an absolute marvel of engineering. So the whole thing really was driven by the case for time domain science. We want a very rapid cadence for short-lived events, such as eclipses and ultra-compact binary systems, supernovae, and then, of course, all of the fast, faint transients, and then detecting microlensing. And then it's deep. Well, we're going to be taking pictures for 10 years. That needs no explanation, right? So through the R filter, it should get down to about 27.5, which will allow us to look at photometric redshift measurement of galaxies, get into weak lensing to map mass distribution, near-Earth objects, all manner of transients. But the takeaway, if you remember one thing from this slide, is this. It'll be about 100 times deeper than the Sloan digital sky surveys. So these are some simulated images. This is 1/4 the diameter of the full moon. It's actually not simulated in this case. From the Sloan digital sky survey, this is simulated data of the same field from the LSST survey. Okay, big data. It's amazing too. Any computer science students in the room? Okay. If it doesn't work out in physics, I'm just saying, Rubin needs you. No. So big data, 3,200 megapixel image, every 20 to 40 seconds will produce more than 20 terabytes of data every single night for 10 years, except when it snows. Millions of transient alerts nightly, processed and sent out within 60 seconds. So I'm going to stop and tell you about this for a minute because it's one of my favorite things. Is the shutter will close on the camera, and then that's the start of the race. And it's about a 2-second readout time. Then the data will flow over fiber to Santiago, to Sao Paulo, Brazil, under the ocean floor to Florida in the United States, over to our data processing facility in Stanford, California. The computer will then look at this image, right? It'll process this, and it will, using machine learning, characterize all of the changes that it notes from the template that we've built up, and it'll classify things. Well, this might be an asteroid, or this might be a supernova, and it's going to automatically send out alerts to people around the world, the world public immediately, who subscribe to those alerts. So it's going to have, oops, wrong slide, wrong button, I mean. Millions of these per night, and those alerts are going to go out within 60 seconds of the shutter closing on the camera, right? Isn't that amazing? There's not that many seconds in a night, right? It's going to be a continuous stream. So, over the 10-year survey, we'll have over 2 million images that are collected of the sky. It's equivalent to more data than 3 years of streaming video, or 50 years of streaming music, if that helps put it into context. By the end of the survey, over 60 petabytes of raw image data. I should have put that in flashing lights. That 60 petabytes is more data than everything that has ever been written down in every language on Earth from the survey. Are you excited yet? Okay. So, where are we? Well, I mentioned Friday, the mirror went in. We're really getting close to completion. It's been a tremendous year of progress by everyone involved. And so, what's next? Well, this slide is a little out of date because I made it before the mirror was in. But I had said all of the sub-assemblies are being prepared. Well, they're pretty much prepared and on the telescope at this point. ComCam, M1, M3, M2 on the telescope. So ComCam is a commissioning camera. It's not the camera we'll use for the survey. It's got the same CCD in it, but only one of them, not 189. So we're doing the final verification on the actual camera right now, but we're going to start commissioning the system with our commissioning camera. Here you can actually see this was 2 weeks ago, I think. So this is the commissioning camera, and this is looking from somebody standing where the primary mirror would be. This is the reflection in the secondary mirror right here. So that is the secondary mirror. And then for scale, this is the camera. You can see the people here, just to give you an idea. This was in the clean room. These are our coding crew, the people that put the silver on the mirror. I love that picture. And for scale, I wanted to show you this. This was in fabrication. This is the first optic on the camera, the first correcting lens. It's the largest optic ever produced. That person is about 5'8". Don't ask me what that is in meters. Standing behind it, about my size. The person's about my size there. And again, here was the picture of the telescope on Friday for the very first time. That's the mirror cell, that's the mirror there, struts, secondary and camera up there. So next week, we hope that we will be collecting photons into the telescope. We're not going to show you what they look like, so don't worry. They'll probably be out of focus anyway. We hope that in around February and March, we will take the commissioning camera off the telescope and put the LSST camera on. It's getting close. And then Rubin First Look. So this is what we are calling our first light, which you commonly hear with telescopes. But what this is going to be is the first look that we give the world of images from Rubin telescopes. So we'll probably collect those, of course, a few weeks prior to that, but we'll have big events around the world for that release. In fact, that's something, Alma, I hope we can talk about tomorrow, is maybe something in Mexico for that event. And then we'll start releasing data. These data previews will come out in July. That'll include scientific data from those public images that we released. And then construction will truly end, and we will begin the survey sometime around September, October of 2025, and then more data. And then we just sit back for 10 years. So, I'm kidding. So I mentioned it was originally the Legacy Survey of Space and Time, and that it became the Vera Rubin Observatory. So it was named by the United States Congress. It's the first observatory to be named after a woman. And it was named after Vera Rubin for several reasons. One is that the dark matter, dark energy is core to the observatory's mission, so it made sense on that front. Because Vera Rubin was the one who took a theory of dark matter that was theorized by Fritz Zwicky, and she made the observations and did the math to prove it. So she's a seminal figure. If she was alive now, she would maybe win a Nobel Prize, or if her work had been done now. She fundamentally changed the way we think about the universe. She was a very strong advocate for women in science. So I was not on the project, but I understand everyone was just over the moon when this telescope was renamed. If you collect coins or currency from around the world, the United States is going to issue a Vera Rubin 25-cent coin this year, probably around the time of first look. So we had nothing to do with that. It's just good coincidence. Okay, so here's how I explain it to my father, in case you're wondering why we have the Vera Rubin Observatory, is the universe. Okay, so when you get stuck on your next physics exam, just draw this, all right? 68% dark energy, 27% dark matter, 5% everything we know about, 0% the things made clearer when you put them on a bar chart. Okay. So this is the mission of Vera Rubin, which I hope I've conveyed, is to produce an unprecedented astronomical data set for studies of the deep and dynamic universe, to make the data widely accessible to a diverse community of scientists, and to engage the public to explore with us. Because this telescope is paid for by the National Science Foundation in the United States and the Department of Energy, the data belongs to every scientist in the United States, every scientist in Chile, and then over time it'll become world public. We're going to talk in a minute about how data, I keep hitting that, is provided to folks here. And so my role is to head the education and outreach. Perfect. And this is also something that's a first for a US government observatory, is that, this is the organization of the observatory. So we have 4 departments: observatory operations, data management, system performance, and education and outreach. It's the first time that education and outreach has been part of the operation of the observatory from the very beginning. And the things that we have to do, that we have to deliver, are just as important to the people paying for this as the science itself. I always like to joke on this slide that, so you can see that all of this, the observatory operations, the data, the performance, feeds the science community, right? And so that's, right now, you know, probably, say, 9,000 scientists around the world or something, maybe 10,000. And my job is the other 8 billion, so. So EPO has its own mission within Rubin Observatory, Education and Outreach, which is to provide online, data-driven experiences that are accessible and approachable, that add real-world context and opportunities for people to engage with Rubin Observatory. The reason that it's mostly online and data-driven is because it's very much a data project. It's also high in the mountains in Chile. So the more that we can do online, right, opens this up around the world. So I won't go too far into this, but we're structured in 4 groups, our staff, and so we have outreach and content, and that really focuses on the general public, people that are interested in science. We have formal education, and so in the United States, when we say formal education, that's classrooms. That's teachers and students. Informal education are places like science centers, planetariums, museums. And so we really are targeting the teachers here, though, in formal education. So we're designing what we call investigations. These are things they can use in their classroom, and they will use real data from Rubin as soon as we can. We have a very large citizen science effort that we're building, which will enable the science community to engage the other 8 billion people in research. And then the technical, which is the least exciting. They're the people you never see because they make everything happen. And so here's the team. This graphic is out of date because we actually have a new software position that's also vacant. But you can see that these are the audiences that we serve: the science-interested public, educators, informal science centers, and citizen science researchers. Okay, but here's the summary slide. Why this is the best job in the world that I have, is to demonstrate how unique and substantial and awe-inspiring this is to the world. And I wanted to mention that we are working hard to figure out the best way to do this in Latin America. And so one of these collaborations is the LSST Mexico collaboration. Okay, raise your hand if you're in the LSST Mexico collaboration. Uh-oh, all right, you need to get them here. So this is a consortium of about 50 members in Mexico that oversee the development of in-kind contributions in exchange for data rights. So these are folks who are developing products to support Rubin Observatory, to support the science community, and in return for making those available, they've got about 20 people working on it. They get data rights for 20 people. So those are 20 scientists that have direct access to the data, the proprietary data. And so what they're doing is they're developing software directed to some of our science collaborations around strong lensing, dark energy, galaxies, and the solar Milky Way and local volume science collaboration. They're also working to promote Mexican community-based participation in the LSST. We are going to talk more about education and public outreach. And then these are the program leads. Alma's sitting somewhere, right there. Okay, so if you have questions, if you want to sign up, you want to make a big donation, talk to her. So some other things, because the telescope is in Chile, we have a staff member based in Chile, Dr. Fernanda Urrutia. She's our Chilean by job title, but also our Latin American liaison. And so she's done a lot of work to begin to expand our programs to Spanish-speaking audiences in Chile and throughout Latin America. One of the big ways that we've done that is through professional development workshops for teachers, as well as building up an online community practice for teachers. And again, these are high school teachers, early college teachers. And you can see if this is wrong, it's all Google Translate, okay? So you can see that all of the web content in our social media is in Spanish. We have Spanish videos. We've started to work in Santiago with 2 museums and the planetarium there to begin to develop content for science centers, planetaria in Spanish. And so we hope that we will begin to bring those things to Mexico, to Brazil, to other countries as well. And then we had the first LSST Latin America meeting this summer in Chile. It's my understanding it might be in Mexico this year. And so we're working to really figure out the best ways that we can use that collaboration to understand how to reach people and to reach them. So yes, I forgot I put this in here. We did a teacher professional development workshop in Chile online in August. But it's open to anyone in the world. We advertise it in Spanish. And we had some like online polls that people could do during and survey. And we asked them, where are you from? And it makes this word cloud. And look what you see. More people were from Mexico than any other country in the online workshop. So we appreciate that it's very important that we access Mexico and that we engage with the people here. We were really surprised to see that. We just assumed that Chile would have the highest proportion of participants. Okay, so I mentioned it's online. So if you go to the website, you can play around, rubinobservatory.org. It actually works better on mobile than it does on a laptop or a big monitor. That was something very early on that we made a decision to do because most people in the world are using mobile devices now. And of course, I mentioned it's all in Spanish and in English. And so on the website, you'll see there's a toggle and you can switch the language. So the website is fully in Spanish. And there's a lot of pictures you can download. And the pictures also have subtitles and alternative text in English and Spanish. Lots of animated videos about Rubin and its science. These are not all in Spanish yet, but we're getting there. These are really good for explaining to your family and friends what we're doing because they're animated. And then we do a lot of science and news releases. These also go out in English and Spanish. And the idea behind these is to familiarize the public with Rubin and really begin to get them excited for what's coming in the next 10 years. The public is they think they're going to see, for example, a picture like from Hubble or James Webb Space Telescope, right? Very detailed, zoomed-in picture of a nebula, right? Whereas, remember, we have a very wide-field camera, so the images are going to look very different. And we're using these series of science releases to help begin to get the public used to the ideas that are going to be coming from Rubin. Okay, and social media. So if you don't, you should follow us on social media. Everything gets pushed out in Spanish as well as English. And I apologize, when I moved this to PowerPoint, I did it on Google Slides. I should have checked it, but it messed up the formatting, but you get the idea. So we actually did an evaluation of our users of the website of social media, and you can see that in social media, only 25% of our users are from the United States. Almost half are from Chile, 46%, and then the other 32% are international. Guess what? That's Mexico, France, and the United Kingdom, and some other countries too. But it's a very international group that is engaging with us, and we're happy about that, right? It enriches the whole project. And the other thing that EPO does is we provide a lot of resources. So again, websites, right? Press releases. Key numbers are fun. You can learn all about things like 3.2 billion pixels and how many TVs it would take. How many corgis, the corgi, the dog, how many corgis by volume it would take to put in the camera is actually one of them. So it's 200 and something. Fact sheets. And then this is probably not the right group for this, but just in case. So as we move towards first look, we are scheduling media visits to the telescope. So if anybody's interested in that, you can go to our website. You'll see this on the website, and there's an expression of interest form that you fill out, kind of what your media affiliations are, things like that. And so I don't know if there's any media here. It's pretty exciting. You just have to get yourself to Chile, and then you get to spend a couple nights up at the telescope and eat some good food. So, okay, formal education. So I mentioned that we've had a lot of response from Mexico, and what we do are develop what are called these investigations. And right now, there are 7 of them on the website. That's the website. Again, it got cut off. And so these are really for advanced middle school, high school, and then introductory astronomy classes in college and university. They can be used online, they can be used face-to-face, and they're classroom ready. So there's nothing to buy, there's no software to install, there's no data to download. You just need an internet connection, and they stand alone, and they take about 2 hours or less. And you can see right now, they're totally free, that we have 3 in Spanish: the expanding universe, coloring the universe, and surveying the solar system. And soon we will have the other 3 in Spanish. I am told that they're actually very challenging to translate because there are many scientific words that are not agreed upon and vary from country to country. So we have a whole committee that reviews these translations. And we do a lot of support for the educators because remember, our audience is the teachers. And so we have tremendous amount of resources, again, in English and Spanish. We have these program guides for teachers. You can see they go through how the things were built and then all sorts of content and suggested sequence for teachers to do this. You can do the investigations yourself. You can just go online, and as long as you got an email address, you log in, and they're fun. They're going to be more fun when we have real Rubin data in there. And we put a lot of energy into supporting the teachers. And so these are some of the ways. You can see that's an in-person workshop. We have, in the United States, we have a Facebook community of practice, an email listserv. All of the online workshops we record and then put them on our website, on our YouTube channel, so you can watch the online workshops at any time. This is a neat map. It shows you these are not people, but they're towns, all of the towns where participants in our workshops, virtual workshops, have come from. And you can see, right, that all of Latin America, and then here is just filled in, right? If you zoom in, it's everywhere. And remember this, because I have a slide with something like this later. But it shows you, right, the demand in these areas is very large. In fact, here's a screenshot from the last online workshop where everybody said they were from Mexico and we thought they were going to be from Chile. And then this is one of our in-person teacher workshops. This was at the Mirador Interactive Museum in Santiago. We had 30 teachers from Santiago that came and participated. And these are all free, by the way, so the teachers don't pay anything. Okay, citizen science. This is where it gets really exciting for you guys, if you're students, if you can't sleep at night, right? If you want to get involved in Rubin stuff. So we mentioned it's going to survey the southern sky every 3 nights for 10 years, right? 9.6 square degree field of view, and it's going to survey 18,000 square degrees up there in the sky relentlessly for 10 years, right? 60 petabytes of data. It just doesn't stop. Wide, fast, and deep. So, I kind of get into that here, right? It's 20 terabytes a night. We're going to end up with 20 billion galaxies, 17 to 18 billion resolved stars, 6 million orbits, up to 10 million alerts of transient events every single night. And again, these are the science goals of Rubin, right? Probing dark energy and dark matter, inventorying the solar system, exploring the transient sky. So we're going to need people. We're going to need volunteers all over the world to help us go through this data, understand it, and make discoveries. I don't do great with math, but I love the title of this slide, right? Trillions of measurements of billions of objects. So every night, right, the Rubin data facilities are going to be processing the images, measuring every object's position, brightness, size, shape. So at the end of this survey, we're going to have, for each of 40 billion objects, 800 to 1,000 measurements, each with a few dozen measured parameters. It's an unprecedented data set. We're going to have thousands of astronomers, physicists, and citizen scientists analyze these measurements. And I should also mention, in the United States, in the United Kingdom, they call this citizen science. We're kind of struggling with that, and we stayed with it, but it's not, you don't have to be a citizen of anywhere, right? You can be anywhere in the world. As long as you're on planet Earth, you can do this. So we don't love the name. We're trying to start calling this volunteers. We may start using that instead of citizens. So volunteer science or something like that. So I hope you understand that this is why it's a great combination, that just the scale of the data is huge, right? We need people to be involved in it and to help us go through it. And it's going to be a huge amount of data, wide variety of science cases to discover the unknown, right? We don't even know what questions to ask yet from what this survey, from what the data will show us. So this is, again, for anyone. So it's for our scientists, right? Because our scientists are going to need the public to go through help them go through the data. We're hoping that this makes its way to classrooms, so students who use our investigations will then take the next step and engage in research with us. And then even for adults, for the public, just to get up close and participate in the research. When people get involved, right, personally, they begin to see the importance of science, and they understand that it's through science that we can understand the universe and the world around us. And that's what we're after at the end of the day, right, is to help people appreciate that they can do science. They don't have to look like us to do it, right? It's just a matter of being curious and interested and taking that to whatever level they want. Oops, wrong direction. Okay. So, another great quote from Vera Rubin: "There is no problem in science that can be solved by a man that cannot be solved by a woman." And I only put this up here because it's really important to the culture of Rubin Observatory. It's not just that we're named after a woman, but we're always thinking about how can we champion the women on our staff, the women in the classrooms that we're in, right? The women around the world who, for the first time, are going to really have democratic access to this kind of data. Okay. So the how of citizen science. So we have partnered with a platform called Zooniverse. I'm sure many of you have seen it. They started with a project called Galaxy Zoo. Anybody do Galaxy Zoo? Yes, good, okay. Do you still do Galaxy Zoo? A little bit, yeah, no, okay. And so Zooniverse is now across sciences. It's not just galaxies and astronomy. But here's the question: does the public really want to look at little black and white moving dots? Well, they do. And in fact, this was this morning. I went to their website to get the latest data. So Zooniverse has had 840 nearly million classifications by 2.75 million volunteers. And this went up from when I first made the slide last week by about 4 million classifications. So I think I'm going to start taking these screenshots and dating them, and then I can see the progression. And people do this for all kinds of reasons. They like engaging with science. They like engaging with the scientists themselves, right? And pretty pictures aren't necessary, right? When people feel like they're contributing to something, they get excited, and a lot of times then they take the next step and they begin to learn more. So as far as what we're doing is we're primarily building this platform to connect to Zooniverse for the scientists to be able to easily get projects up on Zooniverse. So we have a pipeline that will directly connect data from the Rubin Science platform. So that's what scientists will use to the Zooniverse platform. And we're working on a lot of documentation and support for researchers. And the way that that'll happen, I'm not going to get too into this, is through what we call notebooks, these Jupyter notebooks. We have some tutorials. If you're interested, you can see some demos on our website. And the idea is not just to build tools, but that we begin to build a community of scientists and a community of volunteers around the world that are working together, right, to figure out what are those questions we don't know yet to ask. What are these new classes of objects we're going to discover? So it is certainly to support our scientists. It's to reach a broader audience, right? And then it is, again, these challenges of data volume. Right? We're able to use and leverage our social media, hopefully, to bring people into these projects. And again, I think I mentioned we want to connect the citizen science to our formal education program. Okay, back to this slide. So, yeah, it looks like it's night mode now. So again, these are where places where educators have participated in our workshops. And over here, it's not as easy to see, but blue is from Zooniverse, of where their current volunteers are. And look at that. Look where all of our participants are, and very few volunteers in citizen science. So this is something I think that with the LSST Mexico collaboration we should talk about, is how do we begin to get more folks engaged? All of you who are students, right? I want you up all night on the citizen science projects for Rubin. So if you're a person with data rights in the room, a future investigator with Rubin, we should have more information coming soon. But if you want to be in the loop now and practice with some of the notebook tutorials, things like that, we'd love to hear from you. And this is the contact information to get in touch with us. We're testing the pipeline, for example. We're taking 10,000 cutout images from a simulated data set and porting them over to Zooniverse and watching the whole system crash. It's a lot of fun. So, if you're a student, a future volunteer, right, someone that's going to go online and participate in these projects, we're hoping that as soon as we have some pilot projects going, that we'll have a series of talks. We want you to keep in touch with us on social media. And we do have some projects on our website that are not Rubin projects, but other space science, physics projects that you can get engaged with and just sort of get used to the Zooniverse platform. And again, there's websites and bad social media graphic. And then if you're just somebody that, you know, wants to help spread the word, share the hype, is that you can, again, go to our website. And if you have ideas, right, for things that we should be doing around citizen science, we'd love to hear from you. Okay, I did it. Close enough. Okay, so I want to thank you for A, having me, and B, letting me speak in English, because I know that it's not easy. I've gone to a few meetings in Spanish, and it's hard, so yeah. Okay.
Hi, my name is Anna. I'm from UNAM's Astronomy Institute in Ensenada. I have two questions, but the second questions depend on how you answer the first question, right? So you spoke a little bit about surveying for solar system objects, right? And constraining their properties. So at one point in the presentation, you spoke about orbits. And I'm wondering if you're only thinking of studying the orbits of these transient objects, or if you're going to use the Rubin Observatory to study, I don't know, stellar occultations, or some other type of studies to constrain these properties. Oh.
So, two things. full disclosure, my PhD is in education. I am not an astronomer. But I think I would say that it depends on the researcher, right? So we'll have the data, and then whatever research they can do with that data, is up to that person. So the different measurements will be there. Does that make sense?
Yeah.
Yeah,
sure.
so we're not dictating the science that's done. One of the challenging things, though, I am told, is that the camera sensor saturates at like 17th magnitude or something. So, it's going to be a challenge with some of these orbits, right? Because we'll detect the object, we'll move along, and then by the time we come back, we may not be able to recover that object. So,
Right.
but that's
okay.
for smarter people than me.
Okay, thank you very much.
Hello, great talk, great data.
I don't think it's on.
Hello? Hello? Yes? Okay. Great talk, great data. My name is Jesus Hernandez, UNAM. I'm a little worried about the many satellites that are in the sky, and also the space debris that could contaminate the data. Are you worried about? I guess yes, but can you comment about the possible light pollution that can be done for these artifacts?
So to make sure I understood the question, you're asking about satellites and artificial lighting?
Yeah, artificial satellite like SpaceX.
Yeah, so the satellites, right now when they kind of do the modeling, I think the estimate is that we'll lose about 1% of the pixels to satellites. And again, there are, the machine learning and the algorithms to subtract all these things are in place. But they say that, if I remember correctly, it would be very problematic if we were getting closer to 10%, right? But right now they think it's around 1%. The question of artificial light in the night sky is a big one. And so Rubin Observatory is part of AURA, the Association of Universities and Research Astronomy in Chile, with Cerro Tololo, Inter-American Observatory, and others. And they work a lot with the federal government in Chile, and recently they've passed federal legislation around lighting codes and things like that. We do a lot of in-person events and fairs and telescope viewings all over that region to help people understand the impact of artificial light on the sky. The thing that I think is going to make a difference is that I think I heard 2028, 70% of the world's large telescopes will be in Chile. And it brings billions of dollars into their economy. And so more and more, right, the local governments, the regions are understanding the value, the economic impact of astronomy in the country, and that is the reason why I think I'm optimistic things won't get any worse, and they might get better.
Well, hello, my name is Héctor Ibarra from the Instituto de Astronomía de la UNAM. I have two questions related with the instrumentation and two questions related with the data science. The first question is, what is the minimal spatial resolution of the Vera Rubin once you consider the adaptive optics of the telescope?
I didn't catch that.
Okay, what is the minimal spatial resolution of the Vera Rubin once you consider adaptive optics?
Oh, yeah, I have no idea.
The size of the PSF, for example, of the telescope.
Yeah.
Okay,
I'm not sure.
Okay, well, the other is planning to install an spectrograph in the telescope? A spectrograph in the telescope.
There's not a spectrograph on the
Not yet.
on the telescope.
Or there is no plan in the future? No.
Not in the first 10 years.
Okay. And the second is, well, from the data science is, once you have a lot of data that is saved in the telescope, this data will process in the side of the telescope or will be delivered by, fiber optics to another sites? Or, and the other is, can you elaborate, for example, in the case to analyze the data using machine learning in the site? for example, to analyze the data in real time in order to, for example, classify the galaxies using machine learning?
I didn't catch enough of that. Did you understand? It's hard to hear.
Yes, sorry. Using machine learning in order to classify the galaxies at real time in the telescope. For example, instead of using, for example, citizen science, you can use machine learning in order to classify, for example, all the types of the galaxies, or even identify, for example, time domain objects in the same moment that you are taking the data. With machine learning.
Yes. Yeah, so that'll happen mostly in the US data facility in California, but there's also a data facility in the United Kingdom and one in France. And the idea is that, yeah, the machine learning will be saying, hey, this is a candidate supernova, or this is something we've never seen before, and sending those alerts out in real time.
Morning, evening. My name is Joel, I'm from Ensenada. First of all, a wonderful presentation. I think that it was amazing. It was very clear also. My question is about the precision and accuracy of the telescope. You mentioned that the telescope was very fast in order to scan the whole southern sky, but do you have any information about the precision on those movement, on the movement of the telescope, and how to correct that?
Are you asking how precise is it?
The precision of the movement of the telescope.
Yeah, it's very precise. It just like any other telescope, when that has a coordinate that it's going to center on. And I've seen the videos of this actually. It's incredible. So they've attached a star tracker to the front of the telescope. It acquires the center of the field and instantly is no vibration and ready to go. I don't know if that's what you're asking, but yeah. And the fields, I think they'll overlap a little bit as well, but yeah. Again, you could fit 40 full moons approximately in one image, so it's a big area.
Hello, here. So I wanted to ask, you said that through the observatory you were going to take a lot of pictures in about a 10-year time span, right? So what is the observatory going to do after those 10 years? What is going to be the job of the observatory after that?
I don't know, but they're starting those conversations now. There's a lot of people that want to continue the survey.
Okay.
It would take a lot of funding, right? I think this is my opinion. I don't think the U.S. government is going to put this kind of money in a second time, so we'd have to find private funding. But it is possible that that new instruments go on there too. Maybe we have bigger and better cameras in 10 years. Maybe we have a spectrograph. I don't know.
Okay, thank you.
Okay, I'm Antonio. Thanks for the nice talk. I want to ask if your plan in the data releases are to make public the data available for all the community. This is the first question. And the second question is, are those million of alerts each night are real events, or are some fakes, alarms, or something like that? Thanks.
Yeah, so the data's, the alerts that are, that come out in near real time, those are public immediately to the world. So there are alert brokers. I think there's 8 or 9 of them. You create an account and then you get notified of those alerts. But the data, right, the big data releases are gonna happen annually. And you have to be what they call a data rights holder. So if you're in Mexico, one of the 20 people through the LSST Mexico collaboration. But then I think after 2 years, after 2 years, all the data is world public. But it's kind of a scaled approach.
Hi, I'm Ismael Ramos from Puebla. Hi, yeah, you listen to me? Hi, Ismael Ramos from Puebla University. My question is, nowadays, the AI and machine learning is very popular to take the decisions in every day of your life. And what is the real impact of machine learning and in the classification of different kinds of objects in the space? Because you say it's a lot of biggest data. I think capture images, different kinds of images, and is more easy or difficult to analyze the information with IA?
So is your question how much are we relying on machine learning?
Yeah.
So this is not my area of expertise at all. Alma could probably speak to this. Octavio, do you want to? Yeah.
Por cierto, aquí aprovecho nada más, Octavio Valenzuela, que es parte del equipo mexicano en LLST, va a dar una mini plenaria de astrofísica el jueves a las 8:30, y aquí les contesto esta pregunta.
Okay, definitely you should think about if you have like 20,000 million of galaxies observed a few times per week during 10 years, even if you give one of the images to a single person in the world, it's not enough. So you need to make it in an automatic way, in an accurate way. This is connected with the citizen science also questions before. It's not that every single person is going to be classifying galaxies, but you need reliable samples to train the algorithms. And actually, it's a two-way feedback process. This is setting challenges to machine learning community, and also we are receiving a lot of help from the computer science and machine learning community. Sometimes, for example, right now we are testing the visual transformer, which is the architecture behind ChatGPT, for example, to find strong gravitational lenses or galaxies. When data is very large, seems to be more accurate. Another challenge is, if you have those huge images, you would like to split the images in smaller ones, because he mentioned about how huge is a single screenshot. So also there are algorithms to an automatic segmentation to split the images. Also, every night there is going to be like around 10 million alerts, maybe supernovas, variable stars. You need to detect them with very few points to be able to classify, is that a supernova, is that a variable star, is that a solar system occultation? So actually is going to be very useful for us, but also an interesting discovery is that it's very attractive and is setting challenges to the machine learning community also. We can talk more if you're interested.
I have two questions, but the two of them relate to one another. So the first one is, what kind of computer will you use in order to save that amount of data? And given that it will probably be like a very advanced computer, have you taken any precautions in order to make the least amount of damage to the environment?
Yes, so good questions. In California, it's not just a computer, it's a facility. It's a US data facility. It's massive racks of supercomputing power. And there's also one in the United Kingdom I mentioned, one in France. because we want to make sure that if something happens to one, right, that we still have all of the data. And it's a huge amount of energy, right, to run one of these facilities. In fact, Rubin itself. So there is a strong effort, first at Rubin Observatory in Chile. They're right now installing solar photovoltaic panels. Next year, I think we'll be about 40% on that, and within 3 years, we will be close to 100% on renewable energy there. Now, that's small compared to the energy rate usage in California, but they're doing similar efforts in California. They're working to offset the carbon footprint there. But there's not a great solution yet for that, unfortunately, but it's an important question.
Thank you for your talk. One question. If the program is for 10 years, how you will be adapting the new technologies that are growing very fast with your program and data?
Yeah, we don't know what we don't know, right? Just like we don't know what we're going to discover on the telescope. Yeah, I mean, we're having those conversations, right? We don't know in 3 years, you know, the machine learning, right, technologies that we have now, everything could be different. So I don't have a good answer for that. But yes, technology changes too fast even for our survey.
Muy bien, pues ya siendo las 2, pues le damos las gracias aquí al doctor Alan Strauss. Thank you very much, Alan. Y por parte de la División de Astrofísica, pues reitero la invitación a la plática de Octavio Valenzuela y pues a todas las pláticas de las sesiones de astrofísica también. Gracias.